This is 2017, paper 1. It's section B, question 7. The basic idea here is that there are two cities and an equation is given for each city to represent the predicted population growth in that city. So in the case of the first city here, Sapphire City as it's called, the population growth is given by P here. And in the case of the second city, Avalon, the population growth is given by Q. Now in both cases, population growth depends on time, where time is in years. And that starts from the year 2010, it says here. So the start of the year 2010, that's where we set t equals 0. Now, one more point before we start. There are constants s and k in both equations. So what that means is once you work those out for the first time, they're going to be the same for the rest of the question. So getting started, the population in Sapphire City is 1,100,000 people. So what we're being given there is P, the population in the first city. P is a function of T, so we call it PT. We're also being given other information here at the beginning of 2010. Well, as we saw earlier, that's where T equals 0. So we're also being given T equals 0 here. So now we can use our equation for PT to solve for S. So bring down our equation. So it's PT is equal to S times e to the power of 0.1 t by 10 to the power of 6. And we can fit in both of those values now. So TT is 1,100,000 and equals S times e to the power of 0.1 by 0 by 10 to the power of 6. And that's S times e to the power of 0 by 10 to the power of 6. And of course, anything to the power of 0 is 1. So that's S by 1 by, and 10 to the power of 6 is 1 million. So now we have 1,100,000 on this side. And a lot of those noughts are going to cancel. So we've got 4 noughts, 5 noughts here, and 5 noughts here as well cancelling. And we're left with S is equal to 11 over 10. So S works out to be 1.1. And that's part A done. Now in the second part, part B, find predicted population. So again, predicted population is P in Sapphire City. So that's PT is what we're looking for at the beginning of 2015. Now, the beginning of 2015, if time is in years and 2010 was t equals 0, well, this must be t equals 5. So you bring down your equation for P and fill it in down here. So PT is equal to S times, now, and we've got S is 1.1 from the last part, so it's 1.1 times e to the power of 0.1 t by 10 to the power of 6. And of course, we fill in t as well, so t there is 5. So fill in 5 for t. Now, what you can do is just tidy up e to the power of 0.5 by 10 to the power of 6. And if you work all that out on a calculator, you get 1813,593. That's a 5 there, just make it a bit more clear. Okay, so that's the population after 5 years. So it has grown from at the beginning of 2010, we found the population was 1,100,000. Now it's 1,800,000 or so. So it has grown by a significant amount. Now, part C, find the predicted change in population during 2015. So again, what does this actually mean in maths terms during 2015? Well, that means from the start of 2015 to the start of 2016. In other words, from t equals 5, which is the start of 2015, to t equals 6, the start of 2016. Now, we already have the population at the start of year 5. It's actually up here. That was P5 there. So if we get the population at the start of year 6 and subtract our answers, that should give us what we want, which is the population growth during 2015. So let's do that. So population after 6 years is given by the same equation again, just put in 6. So it's 1.1 e to the power of 0.1 times 6 by 10 to the power of 6. So that's 1.1 e to the power of 0.6 by 10 to the power of 6. And if you work that out on the calculator again, you get 2,000,004,331. So after 6 years, the town's population has surpassed for the first time the 2 million mark. So what was the change in that year in between? Well, it's just P6 now minus P5. So P6 minus P5, which is our answer up here, minus our answer here. And if you put those into a calculator, you get 190,738. So that's the population change in the year 2015. Now on to the next part. Now for the first time we start talking about the second city, Avalon. So there's a different equation for that. So let's go back first and find that equation again. So it was Q, so it's 3.9 e to the power of KT. So it's 3.9 e to the power of KT, and it's QT, and it's in millions, so it's multiplied by 10 to the power of 6. Now again, let's decipher what they're telling us. So the predicted population at the beginning of 2011. So what are they really telling us here? Beginning of 2011, that's when t equals 1, because t equals 0 corresponds to 2010. Sorry, t equals 1, I should say. And the population at this stage in this town is just over 3 million there, as we can see. But it's called Q this time, so just be careful with that. So now it's Q, and it's a function of t, of time. So now we fill in those values to find the constant here, which is k. So fill in the 3,709,795 is equal to 3.9 e to the power of k by t, which is 1 by 10 to the power of 6. Now that's just simply 3.9 e to the power of k. Maybe put the numbers in front, maybe put the numbers together, it might make more sense, by 10 to the power of 6, and put the e to the power of k at the end here. So that's 3,709,795. And now we can divide both sides by 3.9 by 10 to the power of 6. So divide both sides by this. So 3.9 by 10 to the power of 6. And that gives us e to the power of k on its own. So now what do we get for e to the power of k? So e to the power of k on the calculator, so let's just work that out. So if we type into a calculator 3,709,795, and you divide that by 3.9 by 10 to the power of 6, and you get 0.95122,948.72 on the calculator. Now, to get the k down from the power, we need to get the log of both sides. So ln is the log we use here, because ln and d are inverse functions of each other. So it doesn't matter which log you use really, but ln makes it slightly shorter. You can use log to the base 10 if you like on both sides. So the ln of that, of e to the power of k, is equal to the ln of the other side, which is 0.95 or 0.95122. So we don't need that many decimal places, because the final answer is only correct 2 decimal places. So we'll just maybe round off there. So maybe round that off to 1, 2, 3. That should be enough. And we will now, there's a rule of logs at this stage, which means the k can come down in front. So this k here can come down in front here. So let's do that next. So now we have k times the ln of e is equal to the ln of 0.95122. 1, 2, 3. And ln of e on the calculator is 1. They're inverse functions, so they cancel each other out anyway. So it's just 1 equals ln. We might as well work out this one now as well at this stage. So it's the ln of 0.95123. And you get minus 0.0499, etc. Goes on like that. So if you round off the two decimal places, you get minus 0.05. Now find the year during which the population in both cities will be equal. So the population is given by P in the first city and Q in the second city. So obviously we put P equals Q here. So write down our formulas again. So once more, PT is given by, we go back to the last page to get this. So go back to the previous page and we find that it's 1.1. So we can use it here. The 1.1 is the value for S. So it's 1.1 e to the power of 0.1t. By 10 to the power of 6. And QT is what we just have been working with there, which is 3.9. It's 3.9 e to the power of KT. Now we've just found K, which is minus 0.05. Multiplied by 10 to the power of 6. Now at this stage they're both equal. So we put them equal. So PT equals QT, which means that 1.1 e to the power of 0.1t by 10 to the power of 6 is equal to 3.9 e to the power of minus 0.05t by 10 to the power of 6. And the first thing that goes is the 10 to the power of 6 on both sides. That's now gone. And we can bring all our e's to one side. T is the unknown we're looking for, so bring all our t's to one side if we can. And the t's are attached to the e's, so that means bring the e's to one side. So divide both sides here by e to bring it over to the left-hand side. So it's minus 0.05 t e to the power of minus 0.05 t. And what that does is it cancels the e's on this side. And as we're at it, we could maybe divide both sides by 1.1 as well. 1.1 on both sides, because that gets rid of this 1.1. And it puts the e's on their own, which is what we want. So now you have e to the power of, and you have e to the power of, there's two powers divided by each other, and the rule for that is you subtract the powers. If you go to your tables, there's a rule for that basically. We can see it down here in your tables on page 36. When you're dividing two numbers, the powers subtract. So that's what we're using. So you can subtract those two powers. The two powers are e to the power of 0.1t, and you can subtract the other power, which is below the line, which is already a minus, so it's minus 0.05t. And that's equal to, on the other side, 3.9 over 1.1. So again, on the calculator, 3.9 divided by 1.1, and you get 39 over 11, which is 3.54. 3.5454. And now on this side, it's e to the power of 0.1t minus minus, which is plus. And if you plus those two together, so it's e to the power of 0.1t plus 0.05t. If you plus those together, you get your answer, which is 3.5454. And let's finish off that. So that's e to the power of 0.1t plus 0.05t is 0.15t. So now up here, we'll bring it up here, we have e to the power of 0.15t. And we have, that's equal to 3.5454. And yet again, we have to get the log of both sides, bring the t down out of the power. So it's the ln of e to the power of, the ln of e to the power of, just there now, ln of e to the power of 0.15t is equal to ln of 3.5454. And we work out the right hand side. So the ln of that, 3.5454, and you get 1.2656. We'll say 57 if you round it off. And yet again, the 0.15t comes on in front, so it's 0.15t. With the log, there's a rule that says that comes on in front always. So it's 0.15t ln of e. Now the ln of e is 1 on the calculator, so that's 0.15t by 1 equals 1.2657. So now it's t finally is equal to 1.2657 over 0.15. And if you work that out, 1.2657, you divide by 0.15 and you get 8.4 roughly. Now, what does this tell us? This tells us that both populations are equal after 8.44 roughly, if you round it off, after 8.44 years. We were asked during which year are they equal? So that's obviously during the 8th year after we started. We started in 2010. So that's, so i.e. during 2018. Now, the next part, find the predicted average population in Avalon. So again, we're talking about Avalon, so use that equation. So QT, once more, is equal to 3.9 e to the power of minus 0.05t by 10 to the power of 6. So that's the population in any given year, t. Now, what they want though is the average over a period of time from 2010 to 2015. So that's basically when t equals 0, the beginning of 2010. And the beginning of 2025 is actually 15 years later. So that's when t equals 15. And they say average population. Now, whenever you see average in an exam question and a function given, that's a clear sign that it's normally calculus, or to be precise, integration that we have to use here to get the average. There's a formula for average in calculus, and the formula is this. And that's what we're going to use here. The average, AVG, is equal to 1 over b minus a, the integral between a and b, of the function. In this case, the function is qt dt. And a and b are the limits on time, which is the variable here. So the two limits are from 0 to 15. So that's what we fill in. So you fill in between 1 over 15 minus 0, integral between 0 and 15 of q, which is 3.9 e to the power of minus 0.05 t by 10 to the power of 6. And that's all dt. Now we'll keep going with integration. So 1 over 15. Now at this stage, there's a technique in integration which speeds things up. Any constants that are multiplied, you can take them outside because they don't affect the overall integration. So you can bring those out. So the 3.9 comes outside, as does the 10 to the power of 6. And you're left with the integral between 0 and 15 of e to the power of minus 0.05 t dt. So we'll tidy up the constants first. You've got 3.9 divided by 15, and we're going to multiply that by 10 to the power of 6. So multiply by 10 to the power of 6. and we get 260,000. So the constant is 260,000. And the integration between, okay, so let's work out this. So to integrate e to the power of minus, that's in the tables, and that becomes itself divided by what's in front of the t. So it's e to the power of minus 0.05 t divided by minus 0.05, and the limits are 15 and 0. And now there's a little shortcut we can use here when there are too many minuses involved, like this minus here, and these limits. The trick is you can swap the limits around if you take out the minus, and it just gets rid of all those minuses. It makes it a little bit easier anyway. So what we write that as basically e to the power of minus 0.05 t over 0.05 to the power of, and the limits are still 15 and 0. And don't forget that's multiplied by, they're still at 260,000 outside. Now, to work out that, so we'll come up here, we're running out of space, so just try and make a bit of space up here. So now we can use upper and lower limits. So sub in the 15 first. So sorry, the limits should be moved around now because of the minus, so the limits are actually 0 to 15. And we will just put in the top limit first now, so it's equal to e to the power of, you put in that 0 and it's just 0 over 0.05 minus, now you put in the 15 as the lower limit, so it's e to the power of, so it's e to the power of minus 0.05 times 15 over 0.05. And now there's a common denominator. E to the power of 0 is 1 minus e to the power of minus. So we've got 15 times 0.05, and that gives us 15 times, that gives us 0.75. So it's e to the power of minus 0.75. And the whole lot is over the same denominator because we've got the same sorry, just fix that. The same underline in both cases is this. And so that's 0.05. And now we try and work out all that. All the time we have the 260,000 out here. So it's 260,000. And okay, so let's just work out that. So it's 1 minus e to the power of, so it's e to the power of minus 0.75. So on the calculator that gives you, okay, so, and we divide that by 0.05, so divided by 0.05. And finally multiply by 260,000. And you get an answer of equals 2743693.9. So what's the question again? So find the predicted average population in Avalon. So I suppose you're on the half to the nearest whole number person. So that's the average population over those 15 years is 2,743,694, rounded off. Now there's one last part to this question. So this time they're looking for rate of change. Now that's calculus also. When they're looking for rate of change here, you want to find out how fast this is changing, how fast the population is increasing or decreasing at a certain time. So what you do here is, again, you start off with your function, and it's the town of Avalon again this time. So it's qt is equal to 3.9 e to the power of minus 0.05 t by 10 to the power of 6. And rate of change means differentiate. So that means get q dash t. And at the beginning of 2018, In other words, when we're finished differentiating, find it when time is equal to 8, because time is equal to 0 in 2010. Okay, so differentiating, again, a constant just stays in front, so that 3.9 stays where it is. Now if you differentiate e, it becomes itself 0.05t, but because of the chain rule, you must differentiate what's in the power separately. So you differentiate that and you get multiplied by minus 0.05. And the 10 to the power of 6 is another constant, so that just stays where it is. That doesn't affect things, leave that out there. And we have to work this out at the time, of course, t equals 8. So it's equal to 3.9. So the rate of change when time is 8, you put in 8 for time, and you get e to the power of minus 0.05 into 8, multiplied by minus 0.05, multiplied by 10 to the power of 6. And when you put all that in the calculator, so there's a minus in there, so it comes out as a decrease. When you put all that in the calculator, you end up with minus 130.712. So that's it. At the beginning of the year 2018, the population is decreasing at a rate of roughly 130,000, 131,000 per year. That's what that figure means. That's the rate the population is decreasing at. And that's the end of that exam question.